This is the first video on problem solving. So a big challenge for many students is how to undertake problem solving. So a lot of students are competent with simple exercises, which means they just repeat the steps that they were shown in a lecture. However, students start to struggle when the question given makes it not immediately obvious how to apply standard methods. They have to do some thinking, or what we might call problem solving. Now, obviously, it's the problem solving skill that is most prized by future employers. And therefore, students' ability to do this, to apply their learning to new scenarios that have not been covered in lectures, is core for their development. So here's an example with a simple exercise. Consider a simple problem where you're given a straight line formula. Here it is, y equals mx plus c. Now, students know this, and they know that m represents the gradient, so there's the coefficient m, and c represents the intercept with the vertical axis, and then they're given a question. Given an intercept with a vertical axis of 5 and a gradient of 2, find the equation for the straight line. Now, clearly, all they need to do is take their standard equation, which they know, and substitute the numbers they've been given straight in. And so they'll end up with an answer, which I've got back to front, and these things just happen. So the gradient was 2, so you've got 2x, and the intercept was 5. 2x plus 5. So that's an example of a simple exercise. You're simply going through the steps. A computer could do that. You don't need to be clever. You're just taking the numbers and plugging them straight in. Now, how does this become a problem? Let's assume that you only know this formula for a straight line, which might be true if you were 14 or 15 years old. And instead you're given a question like this. Given a line goes through 2 points, a equals minus 1, 0, and b equals 3 minus 4, find the equation for the straight line. And the student immediately thinks, I don't know what to do. I haven't been given the gradient information m, I've not been given the intercept c, instead I've just been given 2 points. I don't know how to do this. So this is a simple example of problem solving. Because you've not been given the gradient or intercept information, you might panic because you've not been asked to do a direct copy of a technique learnt in lectures. Instead, you're being asked to apply what you know and use the information you've been given to come up with a solution. Problem solving skills are required. Now, let's look at how you might do this. And again, I'm going to emphasize here, we're going to assume that you only know this equation. Of course, viewers of this video probably know how to solve this already. So we're given a line goes through 2 points, A and B, and we want to find the equation for the line. So the first thing to do is ask yourself several questions and write down the answers. So that's key. Ask several questions. If you ask the right questions, it will be obvious how to solve this problem. Here's the first question. What do I know? Always start with that. What do I know? And in this case, what you know is this equation here, y equals mx plus c. There we go. Next, what information have I been given? You've been given 2 points that line goes through. So write that down. There's my 2 points. And then, does the information I've been given relate to what I know? So you're asking a question whether these two pieces of information are actually linked in some sense. So here's an example. So what do I know? Y equals mx plus c. What have I been given? And what I'm going to suggest you do is look at the information you've been given. So I'm first going to sketch that. I've been told it goes through a point, minus 1, 0, and it goes through a point, 3, minus 4, which should be somewhere like this if I mark some scales on these axes. So I've been given those 2 points. Now I know it's a straight line, and therefore, just by sketching what I've been given, I can see what this straight line will be. So you notice I'm first of all saying, what have I been given? And I'm putting that information down. Now, does that help me? Does it help me relate to the equation I already know? Well, clearly, you can see that you've been given the intercept. That may not have jumped out at you first because you were given it as a point -1, 0, but you can see you've been given the intercept with the vertical axis, so you know C. The next thing is because you've got these points, you can clearly see what the gradient is. That distance is 3, and that distance is 3. So the gradient is -1. So I can work out the gradient is -1, I can work out what the intercept is, and therefore I can write down the equation for this line. Now that was a simple example, but the basic technique will serve you in good stead for many more complex problems you're going to encounter. And my suggestion is you always begin with simple questions. What do I know that's linked to the topic? Write it down in brief before you start reading the question carefully. So as soon as you know what topic the question is about, in the corner of the page, write down what you know about that topic. Now, why is that important? Because that will trigger pattern recognition in your mind as the question gives you relevant information. So if we've done that first, write down what we know, then start reading the question, one sentence at a time. And ask yourself, what information have I been given? Write it down. Don't just leave it on the page. Write it down, because again, that will trigger things. And it will also trigger, how does that information link to the knowledge I've already got from step 1 or question 1? Now, once you've done 1 or 2, what you'll find is that combining the information from 1 or 2, it will largely be obvious, and you'll be able to use that to construct new information. And then, of course, you can combine this new information with steps 1 and 2 and go further on. Now, finally, you're going to be iterating through steps 1 to 3, and it will be slightly different for each problem, but we're going to illustrate this with a number of problems over the following videos, so you get an idea of how to approach problem solving. Here's a different example then. An economist is asked to generate the most profit by deciding the correct amount of articles N to purchase. And here's the interesting thing, is this a good business? That question's a little bit more open-ended, and it's typical of a real engineering problem. I don't just want you to solve an exercise, I want you to give me a sort of vague type of answer. Is this a good idea or a bad idea? So here's the data you're given. The purchase price for n items is this, 100 plus 50n minus n squared. The selling price per item, and that's key, if it's given in a slightly different way, is 100 minus 0.2n squared, and the handling price is 10n. So you want to know, well, what's the best amount of articles to purchase and resell? And we're assuming however many you purchase, you can sell. Right, first pose, and if necessary, iterate through these standard questions. What do I know? What have I been given? And then obviously, question 3 is iterating through 1 and 2. Does the information I've been given relate to what I know? And what new information can I construct from this? So let's have a look. First post the standard questions. What do I know? Well, because we want to know the best number of articles to buy and sell, clearly this problem must be linked to optimization. And that's something that you need to be able to see for yourself. This is an optimization problem, even though it hasn't told you. Now, as soon as I recognize it's an optimization problem, I know I'm going to require gradient information, possibly second derivative calculations, in order to find the maximum or minimum as appropriate. And I could, you'll see I've written it here, if I wanted, I could write these formula down now. What's the formula for a minimum? What's the formula for a maximum? Next, what information have I been given? Well, I've been given equations to represent expenditure and income in polynomial form. And I can use these in order to construct an equation for profit. So there you can see I can use the expenditure and income to form a function for profit. Now, as you'll see when I do this, this function is a cubic. Okay? And why is that important? Because what you've done there, and you'll see this, when you recognize it's a cubic, is you have generated a new piece of information which you weren't given. And that new information will then come with, and I'm going to put it here, what do I know about cubics? So that's where step 3 comes in. When you generate new information, you can then go back to step 1 and say, what do I know about this new information, and does that help me with the problem solving? So here's an example. I know that cubics have got one minimum and one maximum, or possibly in some cases neither a minimum or a maximum, but we'll assume for now that it's a cubic which does have one minimum and one maximum. And knowing that will simplify the analysis I have to do. And finally, here's an interesting piece of information that you might say that's come out of the blue a bit, but this is using engineering common sense. I also know that the optimum number of sales must be positive. All right, that might be rather obvious, but if you write that piece of information down, you'll find it helps. So here's the thing. Always think about your wider knowledge. Don't be too narrow-minded. Sometimes knowledge from totally different fields comes into play. Here, I'm using knowledge about cubics, which is mathematics. Okay? I'm using knowledge about the real world. The number of sales must be positive. And that's one of the skills that you have to generate when you're solving a problem. Always think about it. Is there some wider knowledge I can bring in here? And if I do that, will it make the problem any easier? Usually the wider knowledge you need is pretty obvious. So let's go back to this example then. So we were given a purchase price is 100 plus 50n minus n squared, a selling price per item 100 minus 0.2n squared, and a handling price of 10n. So I can write down an equation for total profit. You see I've got n times 100 minus 0.2n squared, so that's how much I get when I sell n items. I've then got minus 100 minus 50n plus n squared. That's how much I have to spend to buy n items. And then I've got this minus 10n. That's my handling price. Now if I combine all that together, you'll see I get this cubic. And what we said is we want to optimize profit. Hopefully that's obvious. And therefore, what we're doing is a maximization problem. I want to maximize this p. So I take the gradient. There it is, the PDN, and you see you get a quadratic, and the quadratic's got two solutions. Now what do you notice straight away? One of these solutions is negative. And as soon as I recognize it's negative, I use my engineering common sense, which says sales must be positive, so that solution is not interesting. So I only have to consider one of the solutions. Next, I can do a little sketch. Okay? Well, I know that this is a cubic, and I know the standard shapes of cubics, and I also know, if you look over here, that the coefficient of the n cubed is negative, and therefore this function has to be going off to minus infinity as n goes off to infinity, and therefore I know the curve must have this type of shape. And therefore I can see straight away that this point here at 47.4 must be a maximum, not a minimum. I don't need to go to the second derivative information, and that's what I'm emphasizing there. Okay, so I can save myself a certain amount of time by applying general knowledge to this problem, bringing in other information. So there we are, second derivative is not needed. I can see the 47.4 is where the maximum occurs. Now, clearly the optimum number of sales must be 47 or 48 because it has to be an integer. And a typical student mistake is think, oh, the answer is 47.4 and just write it down. And clearly you can't sell a fraction of an item. That's a bit of nonsense. Now the final part of the question, is this a good business? That's the question you were really asked. Is this a good business? Now, I hope most of you would look and say, well, if you're only making sales of 50, I'm not convinced that's a particularly viable business. You're not going to be making much profit there, are you? But that would then lead you to another interesting question. How might I increase the number of sales? If 50 is too small, I'm saying, well, this isn't good enough, but if I could make it 5,000, maybe it is a viable business. So how would I change that 50 to a larger number? And what knowledge do I require in order to do this? And this latter question is actually real problem solving. The real problem solving you're going to have to encounter as an engineer. How do I make the sales higher? What do I have to do? What's going on? Now, let's have a look at the equation we had and analyze it a bit more carefully. So there's my equation for profit, and what you'll see is the bit on the left was the price per item of sales. And the thing is, you'll notice this goes down as the supply is increased. So you pay less per item as you get more items. However, there's something a bit subtle here. You'll notice there's a minus sign in here. And because of that minus sign, if n goes very large, you actually find you don't have to pay to buy the items at all. If you look at the purchase price, which is this next bit here, again you'll notice you've got a minus 100 minus 50n plus n squared, and again you'll know the price per item of purchase also goes down as n increases. And so we end up with some simple observations. If n squared is greater than 5,000, and that corresponds to this bit in here, then the items are sold for a negative price. Now that really is pretty bad business. It means you're paying people to take the items away. If n is bigger than 51, then items are purchased for a negative price, which again seems a bit bizarre, and that comes from this equation here. And so clearly the formula that you've been given are not valid for large values of n. They are too simplistic. And thus in this particular case, you're going to go back to your salespeople or others and say, this data is rubbish. How do you expect me to optimize the number of sales if you give me rubbish data? Please come back with some better formula. So some conclusions. This video has given an introduction to problem solving using some very simple examples. And the key proposal is to ask the right questions and identify what knowledge is relevant. And often this will be iterative. And I'm suggesting the sort of steps you want to do are, say, first of all, what is the topic? And what should I know about this topic? And that could be key formula, laws, assumptions, conventions, and so on. And write these down before you start trying to solve the problem. Next, ask yourself, what information have I been given? And can I use this with what I know, that's just with question 1, to create new information? Can I combine the two? Now, having done 1 and 2, you've created new information. And you might then say, can I use the new information I've got with step 1 to generate even more new information?